Welcome to Logical Verification 2020 to 21, Chapter 11, Section 3. In this video, we are going to cover the axiom of choice. If we recall, if we go back to the last lecture and recall the restriction on large elimination that we had in Lee. So remember, if we have a proof of an existential statement, we cannot use pattern matching to extract the witness used to prove this existential statement. And that's because we would then be able to define a function from a single type, from a type with at most one element, like all propositions are in Lee, and define a function on this singleton type, on the subsingleton type, that returns different witnesses, depending on how the proposition was proved. So if we have, since there are multiple ways to prove this existential, we can, for this statement, we can use any natural number. We can define a function that takes a proof of this existential, of which there is at most one, and returns different values for the same input, which of course is something we cannot have. However, if we're willing to give up this property, then we can make something like this still work. We can still have a certain amount of pattern matching as on existential proofs. We can extract some witness, but it won't be able to get the one from the proof. And this is what the axiom of choice is about. Making this pattern matching here work, but without the property that we get back the original witness. So let's look at the axiom of choice. I mean, those of you who have a bit of background in set theory, this axiom of choice here that we are looking at corresponds to the axiom of choice in set theory. It's pretty much the same thing. Okay, so how is the axiom of choice formalized in Lee? The axiom of choice is an axiom, which says the following: for any type alpha, for any alpha that is a sort, if alpha is non-empty, then it returns you an alpha. And the important part is that we have no idea about what this alpha is whatsoever. We just know that it is an alpha. In particular, it does not depend on how you prove this non-empty. So, how is non-empty defined in Lee? It is just a simple inductive type with a single constructor, but this constructor takes an alpha. Okay, so if we want to prove that the natural numbers are non-empty, we just apply the non-empty intro constructor and give it a natural number, whatever we like. And just to reiterate this point, all of these possible proofs of non-empty are exactly the same. So we clearly cannot have any function that distinguishes this proof of non-emptiness. And also the classical choice axiom does not distinguish between them. So in particular, what we do not have is the classical choice of non-empty intro n is n. This is not true, right? Because this would be a contradiction if we would be able to return different values for the same input proof. Okay, so classical choice just gives us back some alpha. And this is where it gets a bit ugly. So often we want to avoid a classical choice to define data. And this is because classical choice is not computable. So what does computable here mean? means that there is no way to implement classical choice as a function in the virtual machine of Lean. And if you run eval on it, it will hence fail. You can still use the reduction in the type theoretic sense, but it also won't give you a result. It will just tell you, okay, this is defined by choice. So by using classical choice, we can pattern match on proofs and extract data, but we cannot compute with it. In particular, we have no control at all over the result value. And in order to make it clear that definitions made using classical choice are not computable, you cannot evaluate them in the virtual machine, they are marked using the non-computable keyword. So in Lean, we derive various other nice theorems from choice. So choice is a very strong axiom in type theory. It implies a lot of other important results for the theorems. So first of all, the law of excluded middle, so that Lean actually has classical logic, so that for every proposition, P, we have P or not P. This property follows from the axiom of choice, and indeed, the proof of the excluded middle in the Lean core library uses the axiom of choice. Then various versions, you can define various variants of choice. So, for example, classical.sum is exactly what I've referred to previously, that with the axiom of choice, we can define pattern matching on existentials. So this is what classical.sum does. So let us look at the type of classical.sum. It takes a proof of an existential statement and then returns a witness. You will probably not get back the one that you used to prove the existential statement, but it is a witness, but it will be an alpha that satisfies P. And the property that it is a witness, or that it satisfies P, is captured in the classical.sum spec theorem, which then tells us that P is true of classical.sum H. Right? So we do not get the property that classical.sum extracts the witness used to prove an existential, but it gives us back some witness.